this third video, we'll discuss about column generation in the context of our problem, but also in general as a solution technique. So, what is column generation in a nutshell? Before answering this question, let me provide you a more general intuition. In column generation, we need to change the perspective of our problem. And in this particular context, we want to model the movement of a commodity, which in our case, that will be a request, not as a sequence of decision variables based on arcs, but directly as a path. And what I mean with path is we already compute or know a sequence of arcs starting from the source node of the request till the sink node of the request, which is of course connected, and that will be a path. So the overarching idea is to start with a relatively small set of paths for each commodity or request. We solve our problem, we analyze the solution, and given some characteristics of the solution, we decide if there are additional paths we want to add to our model. And we keep solving this model in an iterative fashion until that's necessary. Basically, for each commodity, we are trying to address the following two questions. One, which path among the potential paths I have available for this commodity should I choose? But this is a relatively simple question to answer because that's something our model can already do. And the second question, which is the cornerstone of column generation, is are there more paths for this commodity that I have not considered and that I should add to the problem? So we'll start addressing the first one, and then when dealing more specifically with column generation, we'll address the second question. Going back to our model from the previous video, we need to make a few changes in order to be able to use column generation. First, for our set R of requests, we replace decision variable z AR, which, if you remember, are arc-based because A is an arc, with decision variables z PR. And now z PR, what that is it's a binary, and it is unitary if request R is assigned to path P and 0 otherwise. And two important aspects should be understood. One, how does our formulation change when we apply this modeling change? So when we switch from an arc-based to a path-based perspective for requests. And on top of that, how do we determine the set of paths for each request R? And note that unless the size of the problem is very small, we cannot pre-compute all the possible paths, all the possible feasible paths our request can follow. And if that was the case, most likely we wouldn't need really to switch from our arc-based formulation. Because if that's the case, probably the arc-based formulation is already sufficient to convert to optimality or to a very good solution anyway. So, before checking how the formulation changes, let me show you a simple example. Let's focus on a request with the source node in airport 1 and the sink node in airport 2, and let's assume we have identified these three paths as potential paths for the request to follow. If you see, they're all connected, they all start where they should start, and they all end where they should end. So they are feasible paths for this request. Given these three paths, which one is better? If we define our decision variables as Z115, which would be the black path, Z215, which would be the red one, and Z315, the green one, how do we choose? But on top of this, because this is, as I show in the following, reasonably trivial, not trivial, but easy to solve, are there maybe other paths that you are neglecting and that they might be able to improve our solution? And that's, again, where column generation will really come into play. So going back to our formulation, we need to apply a few changes. In terms of sets, we basically keep the sets we already had, although actually, especially for the arcs, we use them to some extent, but not explicitly. We need to add some sets defining paths. We have set PR, which is a set of paths for request R. We define set P, which is the set of all paths. It's basically the union of all the paths of each single request. And we have a third set, which is PF, which is a set of paths containing flight arc F. In terms of parameters, again, some minor changes. We only change our marginal cost because now we don't we impose it per path. So we have marginal cost PR, which is the marginal cost for transporting request R along path P. And finally, for decision variables, in terms of aircraft, we still retain an arc-based formulation, so X and Y decision variables, they remain as they are. But then, as already introduced, we have ZPR, which is a binary, and it is unitary if path P is chosen by request R and 0 otherwise. And for each request, we have a very special path, which is called PNS, which is the path associated to the no-service arc. Because if you think about it, the no-service arc per se is a feasible path for each request. And we have for each request a dedicated decision variable, which is Z PNSR, and again, if that's 1, it means that request doesn't really travel throughout the network, it is not transported, but again, we decide not to transport it, and the way we represent it is to choose, in this case, a no-service arc becomes a de facto no-service path for that request. In terms of model, these are the changes, something which I didn't mention explicitly, but in red, these are the changes with respect to the arc-based formulation. The cost function is similar, but not yet the same. The first term remains unchanged because that's based on the aircraft routing, and the aircraft routing stays the same, modeling-wise. The third and third terms are the equivalent of the previous model in terms of marginal cost if a request is transported in the network, and the third term is basically the penalty that we decide to pay if a request is not transported, which again in our model means it follows the no-service path. Constraints 1 and 2, they are also unchanged because they define that each flight arc can be flown at most by one aircraft type, and define conservation of flow per aircraft type for each node. And again, they are unchanged because we're not changing anything when it comes to fleet assignment and to fleet routing. While constraint 3 is the weight capacity constraint, but now with a slightly different formula. The right-hand side is the same because we are not changing, again, anything when it comes to aircraft. For the left-hand side, given a specific flight arc, we are basically summing across all requests and all paths of that request, excluding the no-service path that contain that arc. And for those paths, we add a contribution in terms of weight of that request, because it means that request can potentially fly along that flight arc. The fourth constraint is pretty new for this model, and we are basically saying that given a request, no matter how many potential paths we have for that request, we need to pick exactly one. So each request needs to follow exactly one path among the potential candidates we have for that request. So now going back to the two questions I showed you before, we answered the first one. But still we need to determine which paths to add for each request, because how do we know that the initial paths we computed for our request are sufficient? For example, as I said, we could start with a very small set of paths for each request, potentially just the no-service path. But how do we know how to add paths if enumeration is not a good strategy? So that's where column generation again comes into play. This is how column generation works. It looks a bit messy, but I'll try to disentangle the different blocks. First, we need to solve what's called a restricted master problem. Given the solution of the restricted master problem, we need to compute the dual values. So there's a notion of duality, which again I will cover in the following. For each request, we need to solve what's called a pricing problem. And we need to add the resulting path if the reduced cost deriving from the pricing problem is negative. Finally, given all requests, was at least one path added? If yes, we resolve the restricted master problem, we follow this whole procedure again until basically there's nothing more to add. And if that's the case, which is the no arrow on the bottom right, we are done. So first, what do I mean with the RMP, which is the acronym for restricted master problem? It's nothing more, nothing less than the milk formulation which I just showed you with those little changes in red. And that can be solved with a branch M1, right? But in the context of column generation, we want to solve the restricted master problem with an extra feature, which is all integrality constraints must be relaxed. So if we have a binary variable, now we relax it to be continuous within the 0-1 interval. If it's an integer decision variable, we relax it to be continuous between 0 and the upper bound. If it's a continuous decision variable, we do nothing because the relaxation of a continuous decision variable is the same decision variable. But as such, some of our decision variables which we know should be binary or integer will be fractional. So why do we need this if it can cause an issue in our modeling approach? And to do that, before diving into that, let me remind you a bit about duality theory. So when we write a dual problems, we have our original problem, which we also call the primal. When we write a dual problem, we are changing a few things. So a mostly horizontal constraint matrix becomes a mostly vertical constraint matrix. And that's why decision variables become constraints and vice versa. So if the primal has few constraints and a lot of decision variables, the dual will have many constraints and a few decision variables and vice versa. This also means that each constraint of the primal is associated to a dual variable. Then a minimization problem becomes a maximization problem. The objective value coefficients of the primal, they become the constraint right-hand sides values of the dual. And then the objective value coefficients of the dual are actually the dual values of the primal. So basically this is a pretty simple representation. The primal in this case has many constraints and fewer decision variables. The dual will be the other way around. And then this is quite a dense slide, but I'll go step by step. If we are given a minimization problem with an objective as C transpose times X, subject to a set of constraints, classic form AX should be smaller or equal to B, and our decision variables, the only constraint we have in terms of their nature is they are non-negative, we can define a reduced cost vector as C minus A transpose Y, and usually the right part, A transpose Y, we can also write it as Z, where Y is the vector with our dual values, so these values coming from the dual problem. And note that dual values can only be computed for continuous decision variables in a primal. And this is why we need that relaxation in the first place. And now this is where column generation really starts kicking in. For a minimization problem, if we have a non-basic variable, so a variable which doesn't play any role in our objective and in our current tableau, with a strictly negative reduced cost, that is eligible to enter the basis, because the intuition is that non-basic variable having a negative reduced cost, if it becomes basic, it should improve our solution. On the other hand, for a maximization problem, it's the other way around. Any non-basic variable with strictly positive reduced cost is eligible to enter the basis. So in other words, if there's now let's stay within the realm of minimization problems. If there is a non-basic decision variable, which for us is a new path, remember each decision variable maps if a request follows a specific path, where C minus Z is strictly smaller than 0, then that path should be added. Basically, we're using an intuition from dual theory to identify and add paths that seem promising for our solution. Although, and you see that in the dedicated video to the cutting sum problem, adding paths that seem promising doesn't mean those paths will be used eventually. So Here we are back to our flowchart. We have solved a specific restricted master problem. We computed the dual values. Actually, computing dual values is pretty simple. Once you have your primal, commercial solvers can directly output the dual values. For our problem, we need two types of dual values. We have one dual value for each flight arc, eta f, and that comes from constraint set 3, the constraints regarding maximum capacity per flight arc. And we had lambda r, dual values, that's one per request, and that comes from constraint 4, which says that each request should follow exactly one path. And we can use these two sets of dual values to basically compute solve a shortest path problem for each request. And we can do so by defining a new problem. This is actually the pricing problem, where our decision variable, we can call it xa, which is a binary, and it's 1 if request r uses, actually I say flight, but it's flight or ground arc A, and 0 otherwise. And this is a bit how the pricing problem for a specific request looks like. If you see what I'm doing here, and let me use the pen, this first part right here, that's the original cost of our formulation, while this term right here, and this is z. So what I'm trying to minimize here for a specific request is I'm trying to minimize c minus z. And as I said, ideally I want this number to be negative. But are there any constraints? Remember here what I'm trying to find is a new path for a request. So the only constraint I really need to satisfy in this context, and this is also the tricky part of column generation, that's usually how to properly set up the pricing problem. In this case, the only constraint I need to enforce is conservation of flow. So I want to generate a path which is continuous. So it starts where it should start, so in the source node of the current request. It ends where it should end, so in the sink node of the request. And in between, it's a connected path. So basically, I'm imposing this constraint for every node. And remember, here I'm focusing on a single request, so I don't need to specify anything more. And the idea is I'm trying to solve this problem for every request, one at a time. And if for a certain request I get a minimum which is lower than 0, I'm using that intuition from dual theory. I have a negative reduced cost for that specific request. In the restricted master problem, I will add the resulting path. And now it's also clear why in this new formulation that I showed you, in the restricted master problem, I'm not explicitly forcing a conservation of flow for each request. Why is that? Because the way I generate paths automatically satisfies that. So unless I'm really screwing things up when I'm solving the pricing problem, every new path I'm adding automatically satisfies a conservation of flow. So again, just to re-summarize, why do we need a negative reduced cost for each pricing problem? Because from the dual simplex theory, if a non-basic variable has a reduced cost c minus z that is negative, and again, in the context of a minimization problem, then that variable should become basic, which means it should play an active role in our solution. So we start with our initial RMP, we relax it, we solve it. For each request, we use the dual values to try to find a new path. If so, we add all the paths we need until basically we don't find any path of such a kind. Basically, we can still solve the pricing problem, but the minimum value of that pricing problem returns a positive objective. Is it clear now why the whole procedure is called column generation? Because what you're doing is something like this. We start with an initial RMP. This would be the matrix for our constraints. Then, for example, in the first iteration, we had a certain number of paths, at most one per request. It could even be more, but that would be a different type of column generation. We can add some more paths during the second iteration. We repeat the process until a certain point we only had one path, for example, and if we would try to rerun the RMP, now the best path across all requests would only have a positive reduced cost. So this is why it's called column generation, because as we keep iterating, we add columns. And why are we adding columns? Because we are adding a new decision variable, which is path-based. So we actually add a column without affecting anyhow the size of our constraints. Why is that? Because each constraint might have new elements, but we are not adding new constraints because the flight arcs, they keep being the flight arcs they are initially. So capacity per flight arc doesn't change in terms of number of constraints. Maybe we add pieces. Again, the size of the problem becomes, let's say, more horizontal, but the vertical size is fixed. And at the same time, requests do not change. So the constraint that each request should be associated to one path, that stays the same. We're probably adding terms in each constraint, but we're not adding constraints. So I told you that we do this when we cannot add any more path, we are done. But are we really done? Actually, no, because if you recall what I told you, anytime we solve the restricted master problem, some integrality constraints are lost, right? But in the end, we want a solution which is feasible. If we cannot send 0.6 for our request, we cannot send 0.6 of it along a path and 0.4 along a different path. So we want to reintroduce integrality constraints and solve the final augmented RMP. So in the end, we want to solve this problem where all columns have been added with all the original integrality constraints. So if a decision variable has to be binary, it should be binary here. If it's supposed to be continuous, it's alright. If it's supposed to be integer, it has to be integer here. But so basically, we initially relax integrality constraints to compute the dual values and solve the pricing problem, so to add paths which seemed appropriate. But in the end, we want a solution which makes sense physically. But by doing that, by solving this final RMP, reinstating all integrality constraints, do we have any guarantee the solution will be optimal? Actually, no, because we only perform column generation in what's called the root node. To make sure our column generation provides the same solution as the solution we would get from an arc-based formulation, we might need to use branch and price, which is branch and bound with column generation. So we have a tree structure like in branch and bound, and in every node we carry out column generation. But this is, let's say, beyond the scope of this assignment and this course. But long story short, column generation is a very powerful technique for many applications. But in principle, it gives you no guarantee the final outcome is the optimal outcome. Usually you at least get for example, a better linear relaxation or something, but you might need to resort to a more complicated version if you really want to prove optimality of your solution. And this being said, I think this is it for column generation. We have a video that solves the cutting sum problem applying column generation to show you a more practical application. Actually, application is practical, to show you an actual application and an implementation of a column generation algorithm.